watch it later. And today we're going to go through 3 different presenters to talk about different projects that are going on. Abe Stroh from Cornell is going to talk about the smart irrigation project that they're setting up in an orchard. We have Dennis Buckmaster and Andrew Balmos, who are going to speak about the Purdue FarmBeats projects they're planning for this summer. And then we've invited Andrew Nelson to come back and give us an update on one of the smart irrigation projects that Andrew is setting up on his farm. So with that, I would like to just welcome everybody. Thank you for joining. I know we have a lot of the students joining this time from Cornell. I'm not sure if are there any students from Purdue as well, or UIUC? I just want to welcome all the students. It's great to have you on. And please feel free to ask questions as we go. We've asked each of the presenters to spend about 10 minutes giving an overview and about 5 minutes Q&A. So you can use the hand raising. If you guys can all see in Teams, there is a raise your hand feature at the upper right bar. You can raise your hand and ask questions as we go, or use the chat. All right, I'm going to turn it over to Abe to introduce yourself and give an overview of the Cornell work.
Good, thank you. Can you hear me?
Yeah, we can hear you. And if you need, excellent, we can see your slides. I was going to say if anyone needs help with slide presentations, we can do it from our side, but you should be able to do it. Share your screen. Looks good.
Good. Well, so thank you, Elizabeth and Stacy and everyone. So my name is Abe Stroh. I'm a professor in chemical and biomolecular engineering, and been working in towards tools and models of stress physiology in mostly in woody perennials that I'll talk about today, but also some work in annuals, maize in particular. So what I'm going to present is a team that's involved a number of students listed here on the left. I think Glore, Ray, Wei-Chen, and Annika, who is a postdoc and who is actually a plant biologist, postdoc in my group. We represent a variety of expertise, and in terms of faculty, Hakeem from CS, Jose from ECE. On the apple context, we work with Leilang Cheng in horticulture, and on control, to be enabled by an automated system, we work with my colleague, Funchi Yu. And we have a former student of mine has gone out to commercialize this sensing tool, and we're on SBIRs with him, so we're kind of a research and development division in some sense through SBIR subcontracts. So I will talk about this perennial fruit and nut crop context, but generally water is crucial. We all know that. Anyone who's had to think about a lawn knows that if it rains, you get growth. In the context of fruit crops, there's important subtler effects, also in grains, but quality is strongly controlled by water status. Yield, size, shape in apples is very important and controlled by water stress. And across crops, water status controls disease. The context of fruit crops, there's a particular emphasis on quality, and it's strongest and most strongly coupled to value in the red wine grape industry. And what we're showing here is just that everything depends on water stress. And you can see here that, for example, sugars, but other components of a grape that define wine quality don't have monotonic dependence on water. And so there's a need to dial in the optimum in terms of stress. And so here you see stress is measured here, and these are pressure units. And this is the gold standard for assessing the water status of a plant, and in particular, a large perennial that has a distant connection to its soil is in the plant to measure the stress in what's called water potential in units of pressure. And they are, in fact, negative units of pressure, tension. This is the tension in the vessels of the plant that define the physiology all the way to the biochemistry. So the challenge is that although in these crops, in particular in the West, almost uniformly, there's been a lot of investment in a precision delivery of water, there is it's challenging to get to a robust way to inform that with real-time information, and in particular with real-time information about the true in-plant water status. And so there's estimates that we still, even with precision irrigation, overwater by something almost a factor of 2. And that impacts water use. That can impact negatively on quality as well, and management. So why are we stuck in this point where we don't have robust ways to close a feedback loop on water stress? Well, what I'm showing you is what the tool that has given us access over the past half a century. It's been the only tool to give us in-plant water status. And what you can see is a plant scientist interacting intimately with a pressure chamber in which a cut piece of tissue has been placed, and it's squeezed by air pressure. Turns out to be an extremely effective tool, but it is slow and cumbersome and destructive. And so what we have developed is a MEMS solution where we plug a MEMS device into the conductive tissue of the plant to get real time, to translate that stress in pressure units into an electric signal that can then be brought ideally out into the cloud to be analyzed and used to define decision support and even automation. And so we've been doing this across the country, both in California in grapes and almond, and I'll show you some almond data, and here in Ithaca in apple. We've had some success in corn, although it is more of a challenge and less mature in terms of a method, in terms of using this tool. And what you can see here is an insulation of the site in which this MEMS device is embedded in the tissue. So this is an example of the way that a commercial orchard, almond orchard, pays to get water stress data. They have an employee go out midday and make measurements, and typically not very frequently. And so you get kind of an undersampled information about what is the true dynamics of stress. When we come and plug into this, so this is a service that goes up on the web. You'll get information, simple decision support information on too stressed, perfect, too little stress. And this tends to limit how people think about managing irrigation to very simple schedules. You have little information. You're going to act in the simplest way that is compatible with the kind of information you get. And what this tool can do is basically connect the dots. That I think could somebody mute? Is that? Yep. Thanks. And so what you see is that the water stress, actual in-plant water stress, is much more dynamic than is being captured by this low sampling rate manual tool. Every day we have large fluctuations. And then as a function of this irrigation schedule, we have very large changes in the dynamics and deep dives into large stresses. And if we superimpose what UC Davis recommends for almonds, we see that this actually quite sophisticated grower spends a lot of time outside optimum. And so that is one kind of context in which it's a big enough industry with a mature enough understanding of the physiology based on existing tools that we now should be able to target optimal irrigation, either with the right decision support or with full automation of the precision irrigation system. So one of our interests in this is that as engineers, this is a nice dynamical system. It's got the dynamics from the atmosphere. It's got the dynamics of the soil. And we'd like to see whether we can use this now continuous information about the stress in the center of this complex system, the center of the living tree that spans soil to atmosphere. Can we make models that would allow us to go from environmental parameters from a weather station to a real-time prediction? And that real-time prediction we'd like to be able to do in the cloud, for example, to drive decision support. And this is where we've explored this, the theory of this with our colleague Funchi Yu, and to bring what is called model predictive control, where you have a time horizon into the future, where if you have forecast information about weather, you can bring it to your decision today. And so if it's going to pour rain tomorrow, you don't irrigate in the same way on a dry day as if it wasn't going to rain tomorrow, for example. So with that, I'm going to turn to our implementation for this summer, which is built on a prototype that we got up and running at the end of last growing season, and we're refining into this season in the Cornell Orchard, here using Apple as a model, partly because we have this orchard just adjacent to our campus and we have good collaborators on the physiology. But so what I'm showing is the hardware that we have ready to be moved now. Literally Monday, our first access to the field site after COVID shutdown, to be building out a system, a demonstration system, a test system in which to test our hardware, test our ideas of our understanding of the plant dynamics, and the use of cloud services, communications and cloud services. So what you can see now is what we have as the engineering physiology side of this effort have ready to deploy is our sensor embedded in the tree. We have an Arduino-based amplification and microcontroller system. We're working right now with a wired bus that carries both power and data. We use what could be called the sub-edge, which is a Raspberry Pi. And right now we have been using a commercial simple plug-and-play web interface called ThingsBoard. We've also used UbiDots. There are dozens of these Internet of Things services that are quite limited, but very simple to access. And so what we've been working with Hakeem and Jose's team on is bringing this toward access to the full capabilities of Azure and FarmBeats. And this is where I absolutely lose my expertise. And Glore and Hakeem can back me up as I stumble through. Importantly, one of the missions in interacting with the FarmBeats community and team is to create solutions that are compatible with widely used hardware like the particle and the Pi, as well as the FarmBeats sub-edge. Right now, the FarmBeats sub-edge is, our understanding is that it lacks a built-in capability of feedback. So it's a sensor logging system without feedback. And so in all cases, we're aiming at building the abstractions in the cloud and at the edge so that we can be flexible and the community can be flexible in taking advantage of Azure with different hardware. So the types of pathways from, in this case, using the particle. Particle is a commercial category of microcontrollers that has been emphasized web connectivity. But again, this is where this can be a Pi. In particular, we would like the Pi to be sitting at the edge. These are three paths that we've explored to getting to Azure, and we're interested in feedback on this. The webhook kind of standard minimalist solution, it works, but we're not favored. And then among these two IoT services at Azure, we're favoring the IoT Hub for its versatility. And this is the versatility. Our sense is it comes in particularly in getting back to the orchard. again, here to a pi or a particle or even the FarmBeats sub-edge or edge. So this is a place where, again, I'm out of my depth in terms of what sits in all these boxes in detail, but it's a place where we're looking for some kind of conversations we've had in the past about which of the tool sets within Azure we should focus on in order to take advantage of the Azure platform and the FarmBeats capabilities. So we're going to use this setup in the Cornell Orchard. We're going to be deploying our wire-based communications network. It's got some advantages. It's worth considering in orchard context where you have micro irrigation running everywhere. You can run wires. But we're going to use the same sensors and microcontrollers to split off into other communications and hardware solutions, so that we can use the same plant context, the same demonstration site to test out different communications and computations to get to Azure and prototype different ways to use the cloud, the Azure cloud and FarmBeats to support automated irrigation. So with that, I'd be happy to take any questions. I don't see any of you while I am looking at my slides, but happy to have some discussion and feedback on these ideas.
Abe, thank you very much. I'm going to ask Andrew Nelson to kind of jump in and maybe comment. But before I do, I just have a quick question. How many of the MEMS sensors are you planning to deploy in the orchard this summer?
Order 5 to 10. Yeah, and in general, it's our understanding of use case scenarios is that we're going to instrument every tree that we're studying, but that's not the use case scenario in a commercial orchard. And it's one of the reasons why building a cloud-hosted model that can be extrapolated beyond the tree with the instrumented tree is a high priority for us, because the world doesn't want every tree instrumented. That's not practical.
Right. No, that makes a lot of
cool,
sense.
but not practical.
Cool. That would be cool. Andrew Nelson, do you want to just comment? I know you're presenting in a few minutes on your irrigation system, but just in terms of the setup that Cornell is thinking, any feedback?
Yeah, so I struggle with the same issue when setting up mine, and mine goes more over the part that you were just discussing at the end, where, you know, what way do we connect these together, and what makes the most sense. There's a lot of power in multiple avenues, so you can achieve the same result using multiple different ways. It depends what you're most comfortable. You know, from IoT Central, you can use Power Automate to even code-free call different web services, make decisions, and then send off requests to, for example, turn on and off irrigation. I'll show, when I'm doing mine, I'll show the Azure function that I made that does the same thing. It's just, it uses more code, is a little quicker for me to build out, since I'm more comfortable with that. But I'd be more than willing to chat with you after about, you know, the pluses and minuses I saw with both, and like how I'm getting my feedback started. I also provided my code. It's on GitHub that anyone can access, and I think it'll provide like a decent starter for anyone. So that way we can kind of, you know, it's always nice to start from something. You don't necessarily have to use it, but you can go forward.
Yeah, if I may mention, I just Andrew, I've also explored that route of Azure Functions. So now every time, like, I send some stub data to our Azure IoT Hub, and I just grab it off the function, and then based on that, do some computation and send a signal back to a Pi. So we've explored that. Yeah, it's a promising avenue.
Yep.
All right. Were there any more questions? Or actually, well, Andrew Balmos if you want to go ahead and, are you presenting for the Purdue team?
Yep.
Okay, great. If you want to get your
Elizabeth,
slides.
can I jump in with a very quick question? I'm
Vikram,
sorry.
Yes, of course.
Hi, this is Vikram.
Hi.
Hi, Abe. I enjoyed it a lot. So I'm trying to understand. It sounds like from part of what you said that you're using this to sort of offline to build models that can then be used for sort of model predictive control, as opposed to using this actually in live production for controlling an irrigation system. So is that correct, or do you think it would, this kind of sensing and a control loop would be used both? I'm sorry, the control loop would be, but I mean that the sensing would be used in production itself, or would it be used ahead of time to build models?
Well, we're every time we deploy, we think of the sensor in the long term as simply being ground truth on web hosted, you could call them digital twins of the individual plants, and hopefully the orchard scale, spatially and temporally resolved models of the dynamics that's expected. And at that point, the sensing is ground truthing, which keeps the models honest. Every time now in the early days of this, we are maturing the models continuously. And so, for example, interestingly, we have a very good model for in-ground apple. But last year when we moved into potted apples, because we can't generate a drought stress in Ithaca, New York without in ground.
Yeah, we have the same
too much water.
Too much water, exactly.
We found that, in fact, our in-ground tree models failed us, and in some quite interesting, severe ways. That the response to water inputs were not what we had seen. So that's where we stand today. I mean, the vision is that we'll kind of, as we go into a new crop in a new climate with a new management strategy, we will start to build a model there and get it mature, and then we'll be able to extrapolate more easily. And hopefully have relatively low deployment of the instruments in the long run. Yeah.
That makes a lot of
Can I
sense.
jump in?
Thanks.
Can I just jump in real quick? I think that the last thing that Abe said was, well, at least what I heard and what I have in mind is the answer is kind of both, where you have limited instrumentation and you're able to extrapolate over large areas of land, but you still have that ground truth. Because if you depend only on the model could be, well, it is incorrect, right? All models are useful, but they're not necessarily correct. And so you're able to then always correct for that, as long as you have some instrumentation, but try and limit that so you don't have, like we said, in a limit every tree instrumented.
Yeah. The true how by what amount and in how important the improvement of model predictive control relative to good old PID or on-off or something simpler is to be determined. In theory, we show using digital twins in that paper I cited in IEEE, we show that you can do better. Whether it would be better enough to motivate the grower, we do not know yet. That's a research question for this deployment.
Sure. Yep, that makes a lot of sense. Thanks.
Thank you so much, Abe, and Cornell team. We should turn it over to the Purdue team for the next presentation, just to try to keep on track. So Dennis Buckmaster and Andrew Balmos are both representing Purdue. And Andrew, do you want to introduce yourself and take it away?
Sure. So I'm Andrew Balmos. I'm a staff member at Purdue in the College of Ag, as well as a graduate student in the Open Ag Technology Systems Center, which is joint in Ag and in ECE. So I'm kind of an ECE person by trade, working in the Ag side of it now in the College of Ag. So our team's a lot bigger than that. It's much bigger than even this, but these are the people that are in sort of our area that are touching this FarmBeats pilot in some way. And so, of course, you have Dennis and I. Then there's 3 faculty members, and they're the ones that are really doing the research, in which FarmBeats will get integrated into. So the research we'll cover in a little bit. It's not mine, so I'll try my best to at least touch on it correctly. Hopefully not mess up too many of the details. But my role will be to kind of help them get that along, get them installed, data flowing, and then integrating that usage into their research. And so that's Jen, Shalimar Armstrong, and Kita Raturi. We'll see a little bit more about what they do in a few slides. And then there's a few other people. James Krogmeyer is the co-founder of Oats, along with Dennis Buckmaster, that I'm also a student of. And just because of the topics clash, tends to be involved in a lot of these projects as well. And Aaron Waltz is a staff member in the College of Ag's IT group, and he's working on building sort of a data pipeline, and that's how it all kind of comes together. So before we look at that pipeline, there's the good news is we're expecting to get 2 graduate students as well to help us do a lot of things, but also get out there with me and install these farm boxes and make sure the data is flowing and keep it running. So we're excited about getting some extra help as well. So before we get into the research, I try to give you a bigger picture idea of what it is we're trying to build and what we're calling the digital agriculture test beds. So around Purdue, which is right here in the center of West Lafayette, we have 3 Purdue-owned farms. There's a lot more Purdue-owned farms in the state of Indiana. These 3 happen to be relatively close. We've got Acre, the Agronomy Center for Research and Education. That's sort of focused on test plots and doing agronomy, plant science kind of research. We've got ASREC, the Animal Science and Research Education Center, is just right next door. They're kind of charged with growing the grain and the inputs needed for the animal feed. So they sort of operate more like a traditional farm. They're not doing the research on the plant growth. They're just growing it, harvesting it, and then the animal science guys sort of do the research once it comes off the field on how it's binned and turned into feed. So there's sort of an opportunity to look at traditional farming here. And then nearby is Throckmorton Purdue Ag Center, or TPAC, and this is like one of many PAC farms we have across the state, and they sort of operate a little bit more traditionally as well. These 3 farms, though, have a direct connection back to Purdue, a fiber connection, and so we have a very good bandwidth between the fields and the researcher's computer back on the main campus. And so that was sort of a big first step in doing some of this big data research. It's a lot easier to get the data back to the computing now. To complement that, Ag IT installed Wi-Fi. It's predominantly at Acre, where it kind of covers all of the fields at Acre. There is some Wi-Fi down at TPAC as well. And so if you have drones or machine data that you're trying to push back in real time, you've got a kind of a high bandwidth pipe around a lot of the research going on, wireless pipe around all the research going on to get that back as well. Ag IT has a LoRaWAN installation, which covers all of Acre and ASREC, and even reaches down to TPAC. And so that's been really helpful in people sort of going the IoT route, if you will, putting some sensors out there and just getting some data points back at a slow rate. This sort of maybe naturally FarmBeats fits in here, along with a couple other things, where FarmBeats can be one of those IoT hubs that we integrate with the existing LoRaWAN. And so we've actually made some progress on getting Purdue's LoRaWAN and FarmBeats LoRa radio working together, and Ag IT is taking a big role doing that themselves, which is really great. And then finally, to kind of complete the picture, Aaron Waltz's group with the Ag Data Services are working on, along with other people in Ag IT, a data pipeline to bring data from the field sort of into campus and then into some storage into our large cluster computing that Purdue and research computing has available, and then as well as finding ways to aggregate, catalog, and share that data across the Purdue community and even wider outside of Purdue, so that researchers that may not have access to data but somebody else has already taken can sort of leverage it rather than trying to figure out how to instrument the fields themselves for a second time. And then sort of core out that is this thing called OADA, Open Ag Data Alliance, and that's sort of an output of the Oats Center, and it's an API to help kind of bring all that together. And so there's work as this pipeline storage analyzing sort of figure here is being developed. This is an early idea that's being worked on. There's pieces of it that exist and other pieces that are in planning stages. FarmBeats has been a prime user that we've been thinking about. How do we integrate that platform into this system? So that's kind of like what we say, digital ag test beds at Purdue. So FarmBeats specific, we've got 2 test sites already worked out. One of them is going to be at Jinjin's gantry. This is at Acre. It's hard to see in this picture, but it's right behind one of the main buildings. It's this gantry. It's 50 meters long. Mounted on the top here is a visible and near infrared camera, hyperspectral camera. And the camera can move back and forth on this gantry and take 1 millimeter resolution imagery of the plant in that 50 by 5 meter area. And it takes about 6 minutes for the camera to image from one end to the other. So you can get, if you have the ability to collect and store and look at all of it, you can get, every 6 minutes, 1 millimeter resolution hyperspectral image of these plants as they grow. And so they're using that imagery to estimate nutrients and leaf moisture, disease, different stresses, all sorts of sort of plant science kind of metrics. And the idea then is to develop models that connect the environmental condition to those plant state. But their approach is sort of a big data approach, machine learning kind of approach. And so for them, FarmBeats will be the tool that they use to collect the sort of situ conditions. So the soil moisture, the temperature, the air temperature, light intensity, things like that. And that's sort of the impact to them. They need that data. But the sort of benefit to the researcher, which I think is important, that this FarmBeats kind of brings that rolling your own thing doesn't, is that kind of for free, there's this real-time visualization, this dashboard. You can log on and say, hey, everything's working. My sensors are reading reasonable readings, right? There's a ton of effort to go from like a sensor to something like that. And so I think that's one of the, to this particular project, one of its big sort of human impacts is that they can focus on their research rather than on the data pipeline, because while that's research for some people, it's not really for them. And then they would like, though, to see how they can move that hyperspectral imagery data through that same pipeline eventually. So that's kind of the reach goal for this project once we get the environmental data moving. The second sort of test site is also at Acre. This is being done largely by Shalimar Armstrong and Ankita Raturi. They're looking at cover crops. So they're trying to understand how cover crop management affects the variability of the actual cash crop being grown later. And they're trying to build a model that essentially works out how to optimize the right nutrient gains in the ground while limiting the nitrate runoffs in the groundwater. So trying to get the economies of and the growth gains that we get with non-cover crop, fertilizing and things, but also being a little bit more sustainable and controlling the runoffs. So the sort of the impact of the work is primarily to look at that economic model of where it is the threshold, how is it possible to sort of have an economic gain as well as a growth gain and an environmental gain by doing cover crops over the sort of traditional fertilizing schemes we have now? And what does that look like? And to answer those questions, they're going to look at soil moisture and temperatures, air temperatures, nitrates in the water and the soil around it, sort of all the kind of obvious things you would need to measure. And so again, FarmBeats for them is going to be the tool of making a lot of those measurements. And for them, the fact that they don't have to do anything to sort of get the data going, stored, and usable is really important. Here we have Ankita's, this computer science sort of background, and Shalimar is an agronomist, and so trying to get a sensor, hooked to the batteries and to the radio and a script to pull all that data in is just not an impossible barrier, but it's just a complete distraction from their end goal. And so the fact that it kind of comes together is really useful there. And then this project has a potential to sort of spin off some multidisciplinary research. Some ECE faculty and groups over in our Burke Nanotechnology Center is working on sort of novel nitrate sensors that are MEMS devices that are very cheap and easy to print, and they have their own reader for them right now, and it might be interesting to get FarmBeats to be able to read that sensor, and very important to this project. So there's some other opportunities that we might use some of the remaining equipment for. We've got some grain bins at acre, which could do things like insect counting, temperature, humidity monitoring. It would be very interesting. We have a micrometeorology lab from Dr. Grant. Has it out up in one of these fields where he uses, he looks for greenhouse gas emission, and maybe Buckmaster might remember. So it looks for the traditional greenhouse gases, but it's escaping me now. There's another gas which is maybe even more problematic that we don't look at often, that the corn tends to release. And so he's looking at the emission as the corn grows. So he points this instrument across the tops of the fields as the crops grow. And
he's trying to do nitrogen balance on the crops as well.
Yeah.
Yeah.
So there's a very interesting connection between the ag, the environment, and then sensing all that as well. And then there's a project, and we're kind of actually starting to do this one as a side project anyways. We have a tool called IsoBlue that goes into tractors. It logs machine data, CAN bus data, and other sensors attached to it. We'd like to add a LoRa radio to it so that we can either talk to the FarmBeats space station or the Purdue one. And we'd also really be interested in adding a TV whitespace radio for FarmBeats and for IsoBlue. And one of the things I didn't mention, if I just back up real quick, I added these pictures of these towers. Both these farms, Acre and TPAC, have very large towers available for use. This is a WBAA Purdue AM radio station. This is, I want to say it's like 300 or 400 foot tall tower, and this is maybe like a 50 or 100 foot tower. And we even have these mobile towers. So we've got these vertical assets, which are interesting to be able to test, these new radio technologies like TV white spaces. Okay, then finally, I talked about our plan. Not a lot of what we've done. COVID struck right when we were just about to sort of sit down and say where we're going to install these and put them out in the field. And so there's not been a lot of infield progress, but just even a couple days ago, Purdue put out some new guidance on how to get back into the field and on this research. So I think things are wrapping up quickly, and hopefully with our new students, and we'll get out there and get these things going. So that's kind of the brief overview of what the Purdue pilot is.
Andrew, thank you so much. That was great. I know there's a couple of questions that have been coming in, or thoughts. Glore asked, are you leveraging LoRa or TV whitespace for the collection? Given high-res images, the data rates limitations of LoRa, you might experience data rate limitations. So what are you thinking?
So for the actual hyperspectral imagery, Dennis might be slightly more familiar with exactly, but it's the reason it's close to the acre buildings is because that is utilizing the fiber network that's there. So I don't know if it's Wi-Fi from the building to it, or if we've brought hardwire out. But for the actual imagery, we're not using the radio. But for IsoBlue, where we're looking at CAN data, which is sort of a medium-sized data, it's probably too much for LoRa, but it's not megabits and megabits a second. That's where we're really interested in the TV whitespace. I think being kind of right there, it's got the right range to cover rural, and it's got the right speed to really kind of do real-time machine data stuff, but not, and there's a lot of agronomic stuff to learn from that, especially, as you drive through spraying records, planting records, and then your harvest records, and all that sort of comes together to really build a good agronomic model.
So IsoBlue, what sort of bandwidth does it need?
So if a standard machine that has 2 CAN buses running at sort of the ISO standard rate, which John Deere actually goes faster than that, that's 500 kilobits a second max, right? So it's not a huge data stream, but it's a little bit above there. But we're doing other things too, like putting video cameras into the cab, do image processing on what's the operator doing, why'd they make this decision, what's the field look like, or the crops look like. And so then you start talking about needing, maybe 1s to 10s of megabits to do a good job.
Yeah. So that would probably require the newer. There is newer release TV white space hardware can do up to 100 megabits. So
we just had a call the other day, kind of discussing TV white space and what to do, because we're putting an application in, and we became obvious. We kind of have two needs. There's the narrow band and the wide band, and for FarmBeats, the narrow band makes a lot of sense, but I think maybe for something like ISO Blue, the wide band's more appropriate.
Yeah, for your grain monitoring, like narrow band would make sense. I'm actually that's the planned addition to my farm for this year is narrowband TV white space to grain monitoring.
Cool. Yeah, we should. I'd like to stay in touch with you on that. I know. Dennis has mentioned a few times that they. I'm relatively new to the College of Ag, so I'm still trying to remember people's names. I've been doing it as part of OATS for a long time, but there's all of a sudden a whole lot of new people. But I know there's some interest in instrumenting them better than they are now.
Mm-hmm.
I think they have instrumentation in them, but the connectivity is really awful. And I think essentially they VPN into a computer that's just in a shed by the bins and literally use a GUI window, program to look at the data.
There's a question about the new TV whitespace. Andrew, is the newer TV whitespace hardware available now to try out?
Sounded like it was. I'm trying to remember the name. I'll post it in the chat when I get it. I want to say the company's name is Redline.
Okay, great. All right. Any other questions for Andrew Balmos on the Purdue work? All right. Well, thank you. Thank you so much, Andrew and Dennis. And for our last presentation today, we're going to turn it over to Andrew Nelson to talk about the closed loop irrigation system that he's been working on this summer out in Eastern Washington.
So I will preface this with we have had a lot of rain here. So
you haven't gotten to
it hasn't been irrigating that much. I actually tweaked it up so that way I could at least make sure it's working. But just a second, no, let's share my screen. All right. Can everyone see it?
Yep.
Okay, so how I like to start all of my talks. This is my field yesterday, my Austrian winter peas. They look great because it keeps raining and raining and raining and raining. It's been blooming for 2.5, 3 weeks now, and I'm guessing it's going to bloom for another 2 to 3 weeks. But that just kind of highlights that the real world clouds are causing issues with my digital cloud computing. So, I just want to go through the system diagram that I have. It's pretty simple here, but that's kind of how I wanted to start out with, especially with this closed loop irrigation, where I start with something simple, so that way, everyone has something to work from, and the code's on GitHub, and if there's any questions, you can feel free to email me about it. But I just kind of wanted to make something that is a good starting point, and decently flexible for different ways to use it. Mine's irrigating my orchard, but to be honest, it is flexible enough where you could put it on corn or anywhere. So basically, you just need the FarmBeats sensor, and then you need a way to control your irrigation via the web. Those are the main things. So if you look at my connectivity diagram, if you joined the last call, it looks pretty similar. I am limiting it to just this sensor irrigation on my orchard. So I have the sensor station in my orchard. All I have right now connected up to it is soil moisture. It's measuring the soil moisture right now at about a foot down, and I'm just trying to make sure that my trees have ample water. So that sensor station, the orchard, connects back to my LoRa subedge. The main reason I'm using LoRa is because I have a LoRa subedge right at my office, and the orchard is close by. So it could just as easily connect over the TV white space connection too. I have LoRa right here. So that is why it's connecting up to that. And then from the LoRa subedge, it goes up to it's in my home office, and then the data goes up into FarmBeats. So in FarmBeats is where it's storing all of my sensor data. And then I have my Azure function pull information out of FarmBeats. And then there's a very simple function for my decider on if it should irrigate and how long. So that function will run, and then it'll tell the irrigation control service, hey, run for this long. It could also, if it's a simpler irrigation system, it could just say, turn it on now, and then as it's as the function runs again, it could say turn it off now. So that's how I have it set up as of right now. The Azure function is pretty simple, which I'll go into later. I just want to show the quick setup. I'm lucky I have a smart irrigation system for my lawn. So I actually kind of hacked it to use it for irrigating my orchard too, because it happens to have a API that I can call. So that way I could abstract out that part of the process. It uses, normal drip hosing. Each tree has a 3-foot perimeter of drip line irrigation around it individually. And then the middle tree in the orchard is where I have the soil sensing on. And if I were to put like a plant stress or something like that, I'd probably put it on that one to get the best representative tree out of all of them. You can see my very simple sensor station there. Once again, I love putting these things on PVC because they're so easy to move in and out. Whenever I'm, clean up weeds or if we need to spray something down there or something like that, it's just been very nice to quickly move it out of the way.
Andrew, just a quick question. What slide are you showing right now? I'm seeing the orchard connectivity diagram.
Well, that's not right. I'm showing, can you see it now? All right, well, I guess I'll reshare. Can you see the station setup now?
Not yet.
I don't see anything yet.
It's coming. It looks like it's coming. We just have maybe a slow. Right now
okay.
it's just
try a different way of sharing it, and then there always has to be one that has technical issues.
We're doing so good.
Yeah.
You
Can
need
I
to
ask
use
a question while
TV
you're-
white space to connect.
Yeah. Can I ask a question while you're bringing that up? Is your irrigation control system on the network? You said it's a smart device. Does that mean that it has a network address, or is part of your home Wi-Fi, or?
Yeah, so it connects up to my home Wi-Fi. It's called Ratio. It's just a smart irrigation for lawns, actually, but it just has a simple control, to do any sort of irrigation control valve. So this irrigation water comes off of a different pump than my, home watering. So I have a lot more flow through here. I can turn both of these irrigations on for my orchard and for my small plot of corn, and it runs just fine. The nice thing about it is, there was available API for me to call for it. Can everyone see my
Yes, I can see your pictures and your station set up in your irrigation.
Yeah, so it's a pretty simple setup, but the idea is more of you know, the function and what I have available on GitHub, and then, you know, as things are going through, I'll be using the Azure weather service to, you know, to do some more smart parts on it, and also logging when I'm irrigating to data tables, so that way I can run some analytics on it. I also have full-fledged sensor stations that are within, you know, a quarter mile of this one. So for wind speed and stuff like that, I'm taking it off of there, since, you know, a station inside the orchard doesn't work quite as well for that sort of data collection. So as I said, the code is available on GitHub. And I right now just use it as a HTTP function. So you can deploy it out. I also have this deployed out to our Azure instance. And so I have a daily run on it, but you can have a IoT Central event, you know, through Power Automate call Azure functions as well. So that way you can have these show up and being able to easily call your code or call, you know, your logic behind your irrigation decisions. The valves I'm using are just Rainbird valves. They're nothing special at all. I kept the cost of my system pretty low, but you know, they're suitable for the amount of trees I have. So I'm running 5/8 inch drip line irrigation, so I get enough flow through those. And then that was about it. And I will also post in the chat the GitHub link to be able to access the function code. And if there's any questions on it, feel free to reach out. And it's just, we're wanting to provide a quick and easy, you know, starting point for some of this stuff. And like I said, I'll probably be updating it slowly as we get drier. But the hard part is right now, all of my decisions are don't water. So, and I do store all of the soil moisture data. So that soil moisture, we got a question: as the soil moisture data goes to the cloud, do you store any of it, or is it gone as soon as it triggers the function? No, it's all stored in FarmBeats, and then I'm just grabbing the most recent values when I'm running my irrigation decision. Since with my irrigation pipeline, what I'm doing is I am reading the value and determining the length of time to irrigate. I don't want to run that function, you know, 100 times a day. I'm really just running it twice a day. Check what the moisture is, run it, and then that's where I'm going. The next phase of this is to store the data, so I have the runtime and the moisture percentages for before and after, so that way, you know, run correlation, make the function smarter as time goes on. So that way, when you're trying to hit a target, it can always hit that target.
All right, great.
There was a question: what type of valve are you using?
So the valve is just a Rainbird valve, 1-inch valve. They're very simple valves. All they need is a control power, and it'll turn on when you complete the loop of the 12-volt power. So it's quite easy to get them to turn on and off.
And then I have one more question about reliability. How do you, is there any fault tolerance in there at all that ensures that the valve actually turns on and that actually turns off in confirmation?
So there isn't confirmation now, but that would be coming through with the validation when I start saving the information in the tables for watching the soil moisture. So if the soil moisture is not increasing over that time, you should know, that day that there is an issue.
All right. Any other questions or comments or any questions for any of our speakers today? All right. Well, Andrew, thank you so much. Hopefully you'll get some dry weather. Test it.
Hopefully in July.
But that's great. And thanks for sharing the code as well. So I think our next FarmBeats community meeting is set for July 23rd. We're doing these monthly right now. And we'll invite some guest speakers for next time. If you have any topics or if you would like to give a short presentation, please email us and let us know. Thank you very much, everyone, for speaking, and thank you for joining us. Good luck getting everything out into the field for those of you that have been waiting.
Thank you, Elizabeth.
Thank you, Elizabeth. For
Thanks.
organizing.
Had a very helpful session. Yeah, really appreciate it.
Great. Thank you, guys. Have a good afternoon.
Thank you.